Hello mathematicians. This next little bit, if you thought your head hurt before with transformations of graphs, this is really going to hurt. Sorry. So, consider this function. So this can be a parabola, straight line, exponential, hyperbola, etc. Then if we multiply that function by a constant, what we do is stretch the graph vertically by a factor of a. This little bit down here, probably don't need to worry about too much. It's really more for extension 2. So we'll just stick with this. We stretch the graph vertically by a factor of a. Now, we'll just look at some simple examples. There's a more complex one down below. But if we look at, first of all, say a straight line, simplest example of the lot. If we have y equals x, we know that that graph looks like that, the line passing through at an angle of 45 degrees if both axes are equal. If we multiply that by a constant, say make it y equals 2x, we know that that means the graph gets steeper. And making the graph steeper is like taking this and stretching the graph out vertically. So if you imagine this was rubberized and getting hold of the top and bottom here and stretching it out, you can see that this is what we would get. Think about it maybe with a parabola as well. Here's y equals x squared, like a simple parabola. There's y equals x squared. What does y equal 2x squared look like? Well, it looks like this graph, except it's narrower. That's how we described it before. And it's narrower because we've effectively stretched the graph vertically by some factor. If we take the function of x on a, that stretches the graph horizontally. So again, if we stick with some simple examples, if we replace x by x on 2, for example, then we get this. Y equals x on 2. If I just change the pen colour, y equals x on 2 is going to look like this. Its gradient is now only a half. So that's the same as if I grabbed hold of the graph here and here and stretched it out horizontally. So again, imagine it on a piece of rubber and what happens if you stretch it out. For the parabola, if I replace x by x on 2, it becomes the graph of y is x on 2 all squared, which is x squared on 4. The effect of that is to flatten our curve out, is what we would have said. But again, that's the same as taking this original curve and stretching it horizontally. Now this is not really commonly encountered at all. I'm just including it for the case of completeness once again. Now the next little part of this takes a long time to say. It's quicker to think about. It's a little bit useful in extension 1. It will be very useful for those of you who go on to extension 2. So if we're graphing a reciprocal function, so y equals 1 on the function of x, then the process is to initially graph the function and use the concept of reciprocals at key points. So these are some things to consider. Where the function equals 1, so that's the y value, remember, f of x is the y value. So where the y value is 1, then 1 on the y value, 1 on the function, is also 1, because 1 on 1 is 1. Between 0 and 1, then 1 on a function is actually bigger than 1. So say we took the y value of a half, then 1 on a half is 2. So we increase the y value. As we tend towards 0, from the positive side with the y value, then 1 on the function tends toward infinity. Because we're dividing by an ever smaller number, it's a positive number, so we'll get an ever bigger number. Where the function is positive, then 1 on the function is positive. Where the function tends towards infinity, then 1 on it will tend towards 0. Where the function is greater than 1, then it will now be less than 1 when we take the inverse. Where the function equals 0, then 1 on the function is undefined, as we've seen. That won't be a possibility. these other ones here, as we tend towards 0 from a negative side, so we're taking smaller and smaller negative numbers, then 1 on really small negative numbers becomes a really big negative number, minus infinity. Where f of x is less than 0, then 1 on f of x is also less than 0. So where f of x is negative, so is 1 of f of x. And finally, where we tend towards where f of x tends towards negative infinity, 1 on f of x will tend towards 0, but coming from the negative side. Now, how do we put all of those things into play? Well, here's this example, which I'll try and talk through, and every example is going to be slightly different. It will involve some sub-selection of these things. So, putting the points up above into place. So here was our original curve, y equals x outside of 4 plus x. It's a parabola which is going to cut at 0 and minus 4. It's concave up, so it has some positive bits and has some negative bits. Now, where we have the original function equaling 1, which is going to be just here and just here, it's going to have a y value of 1, then the reciprocal has the same value because 1 on 1 is 1. So they have those points in common. Where the original function equals 0, then the reciprocal function is going to tend to infinity. So it shoots off up here. Minus 4 will in fact be an asymptote, and 0 will be an asymptote as well. Where the original function shot off towards infinity and it was a positive, then 1 on the original function tends towards 0 and it's a positive. So we have these two asymptotes heading towards the x-axis from above. Where the original function had its minimum value of minus 4, the reciprocal function will be minus a quarter, minus 1 over that. And where the original function was minus 1, then the reciprocal function will also be minus 1. And as we get closer to that asymptote from this side, we're going to drop off to negative infinity. So it's really just looking for clues at the moment to try and sketch this curve up. It will become easier later on when we have calculus, but for the moment we're just sifting through these clues, thinking about what would happen with points that got closer and closer to points of interest. So clearly 0 and negative 4 are points of interest because they are restrictions on the domain of our reciprocal function. Now this last example is really dipping into the realms of extension 2, but it's useful background for those of you who are thinking of doing that. So we've got two functions, y equals minus x, which we know is that horizontal line there, and y equals 2 to the x, which is our exponential function there, and then we're going to try to graph y equals 2 to the x minus x. So that is really the sum of those two curves there. So to graph sums, or differences for that matter, we use a technique. So for those of you who are in physics, you might have used this technique called superposition, where we just add coordinates and we try and do a dot to dot. So where two curves intersect, like here, oh, well no, so those two curves don't intersect there. Where those two curves intersect there, the height of the resultant will be twice that. Where we have one curve being 0, then the total height of the curve is the height of the other one. And as we just dip further and further down here, this curve is increasing more rapidly than this one because it's raised to a power. So the blue curve eventually gets closer and closer to the orange curve here. Over on this side, the value of 2 to the x gets less and less important. It's getting towards 0. So the blue curve tends to get closer and closer to y equals minus x. Now it's a little bit of mumbo jumbo and voodoo at this stage. So let's just say that if we are unfortunate enough to get one of these, and 99.9% sure that won't happen, then we just look at key points and imagine adding the y values together. So have a go at these. I hope that I've selected ones which are reasonable, which reflect Extension 1 standard, but let me know how you go.